Now again, welcome everyone to this second talk actually of the current series of our EDT community. Most of you, I think, are familiar with the concept, with the people behind it. After the last talk of Francis, which was very interesting on optimizing DevOps processes. Today we have, in my personal view, also a very, very interesting talk by Shaukat Ali. But before going into that, let me give you a quick overview of what will be ahead in the series. We have what to do today, the talk by Shaukat. Then in 2 weeks, we will have a talk on enterprise digital twins by Vinay Kulkarni from Tata. Then hopefully by then we will get a confirmation for the talk in 4 weeks, which will be on November 14th. And then, as always, after these 4 talks, we will do a wrap up of with all the presenters actually of this series, but also of the last series. So there will be a very big discussion on the topics that came up in these series on November 28th. But with that being said, let me introduce today's speaker, Shaukat Ali, who is head of department at Simula Research Lab, where he's officially having the position of chief research scientist with the main research focus on the verification and validation of cyber-physical systems. But the main or where he has done many contributions as far as I know and have seen in the areas such as search-based software engineering, model-based systems engineering, but also very interestingly, also compared to the speakers we had so far in quantum software engineering. And of course, he is also a program chair of many big conferences and also has been reviewer of many big journals. But I think I will leave the rest to Shaukat, where today he will be talking about AI-enabled digital twins for cyber-physical systems. So Shaukat, I will stop sharing my slides and the stage is yours.
Thank you very much. Thank you very much, Daniel, for a very kind introduction. So I will share my screen now. All right, so can you see my slides now?
Yes, at least I can see them.
Okay, perfect. So thank you very much for the organizer to giving me this opportunity to give this talk. So in this talk, I'm going to present a line of work that was done by our PhD student, Xinhua, who is a PhD student in our department. And the topic is about AI-enabled digital twins for cyber-physical system, where we try to build digital twins directly from the data. And we also try to build some functionality also using AI techniques. So I'm not sure if you guys are familiar with Simula Research Lab, but I'm going to say a few words about my department on the type of topics, and then I will continue on the topic. So in our department is called Engineering Complex Software Systems, and we are focused on building complex software systems, including different activities such as design, development, testing, operation, and maintenance of cyber physical systems, and so on. So mainly in most of our work, we focus on classical system, but in the recent years, we have also been looking in quantum computing, and in the long term, we also envision to see that quantum computing could also be a way to simulate and could be part of, in the future, the digital twins that we also envision to see it. So we focus on both classical and quantum computing domains and also their interactions in the recent works. So we focus on different domains we have worked, such as in healthcare, welfare, transportation, autonomous driving, and we're focusing on different paradigms as we are going ahead in our research. On the left side, you can see that these are some of the real world systems that we are currently working in our department, such as we have a set of autonomous rovers in our lab. We also have some medical machines from Oslo Commune or Oslo City that we work with on making their digital twins and testing and so on. And through EU projects, we also have access to elevator domain, and also through a collaboration with Nordic projects, we also have access to some quantum computers where we can do some computation as well as we need it. And we focus on all the different phases of software system development, including requirements, design development, and so on. So we apply different methods in our work. So we do a lot of model-based engineering, where we try to capture our system in models. And we have been doing a lot of manual modeling in the past, but we are also started to recently look into data-driven and data-augmenting modeling so that we can complement both kind of models. We have done a lot of software modeling, but now we are also looking into modeling hardware and some aspect of networks and so on, and focus on variety of regions such as closed systems, dynamic system modeling and simulation, and so on. And digital twin has been one of my favorite topics in the recent years, where we are trying to build some digital twins with model-based system engineering, and then also trying to build this data-driven and data-augmenting modeling as well, which will be the focus of my presentation today. And we also have been investigating how can we evolve these models automatically so that we don't have to manually redo the modeling when digital twins evolve. We also focus a lot on decision making with uncertainties, which has been a key area of interest in our group. And we want to maximize the autonomy of the decisions which are made by digital twins. We do a lot of applied AI. It means that we take existing AI methods and try to solve different problems in systems development and so on. We have applied a lot of these methods for optimization tasks, for example, test case prioritization, minimization, and so on. And we have also applied reinforcement learning, deep learning in the case of autonomous driving. And with this, I will go towards our work. And since we are focusing on building a digital twin, so we focus on different type of systems in our work. So in the first piece of work that we did, we focused on this water distribution and treatment plants. And we had access to these 3 plants. And actually, these are the plants which are maintained by a lab in Singapore, and they focus on water treatment, water distribution, and so on. So each of these system has a set of sensors and actuators and so on that are attached to them. So our idea was, how can we build digital twins for these kind of water and distribution and treatment plants and do different tasks? And the task that we focused in this work was on anomaly detection, that is some abnormal behavior. And in particular, we focus on detecting security attacks on these plants before they actually happened. So some of the background. So when we have to build digital twins from data, it means we need to have access to the data that we had in this case from these plants. So as I mentioned that we had different kind of sensors and actuators. So for example, on the top, you see 2 of the sensors which are monitoring some values, and we have 3 switches which are kind of actuators. And then we had this kind of data initially available, which was labeled by these test beds. So for example, the first column shows the time. So it's a time series data. So at 10 o'clock, we have the different values of sensor and actuators and the label associated with each row. And these are the sensor values. These are 2 I shown here. And then we have 3 actuators whose states are shown in these 3 columns. And finally, we have labeled assigned to them whether each sample has a normal or is it attack or not. So this kind of time series data was a key input for our task to build a digital twin. So when we try to apply these methods, for example, this example of applying a machine learning approach, we have a neural network, so we have different set of layers, and let's say we do a classification task. So when we tried to build, we found there were several challenges in making digital twins in this case. First of all, when you have the data, it's not necessary that the data will be capturing the special features, such as the relationship between different sensors and actuators. Those kind of features are not explicitly captured in the data. The second issue was that there's not always a sufficient label data, because we start with building our digital twin from the label data, which was provided by those test beds. But then we wanted to make our digital twin more live. So it means that the new data, when it comes, it doesn't have any label associated with. So we wanted to somehow also have this technique to automatically label the new samples or new data which is coming from the operational systems. And third important thing was learning during runtime. So it means we want our digital twin to be operating on a real time of data which is coming from the system. So to solve this challenge, we went on implementing our first technique and that I'm going to present. So we viewed a cyber physical system operation, we call it a physical twin. Let's say in this case, it's a water treatment plant. And it produces this live data, which comes to my digital twin, and digital twin shall be able to take some action in certain cases on the cyber physical system in operation. And digital twin has a model which is representing the live system. And according to one of the definitions, there are many definitions, but it's kind of a live replica of a cyber physical system, and it has some sort of a capability. And in first series of works, the capability was anomaly detection that we implemented. And digital twin model and digital twin capability, they interact with each other. So because digital twin capability needs to interact with the live model of the twin. So in work, we implemented a neural net. In the first work, we implemented a neural network-based digital twin. So this was my diagram. This is one of the view on how we view a digital twin. And then in this case, we implemented our model as a timed automata machine, initially from us data which was available to us. And the capability of anomaly detection was implemented as generative adversarial networks. How does it work? So we have a cyber physical system, and then we have two types of data available from it. First is historical data, and second is the real-time data coming from the cyber physical system. Historical data is the one that I've showed you before, which is a set of time series data which have some label associated with each sample, that whether it is normal data or is it an attack. So that's the historical data. So we use that initial, and these are two things. One is the model, second is the capability. And then we use this historical data to build an initial version of a digital twin model. So we use an existing algorithm was about making a timed automata, and then we extend it a bit to deal with this to make it more probabilistic. So first set of digital twin comes from this historical static data that we have available. Once we have that timed automata, then what we need to do is we need to fine tune this model based on real-time data so that we want to make it live, so that the model is continuously reflecting the current state of the operational cyber physical systems. The second thing is digital twin capability that is purely based on the live data. So we use GANs or generative adversarial networks to build this capability. And GANs have two key components. One is generator and one is discriminator. The generator is a component that takes certain piece of noise as input and it produces fake unlabeled sample. Then this sample is not labeled yet. So it's we did small variation to existing, for example, sample and come up with a new sample of data. Then we use the live model from digital twin as a ground truth, because if it close to ground truth, it means we can try to somehow come up with the label of this this data, this sample. As a result of ground truth labeling, we can have a label assigned to this sample. Then this is given as input to discriminator. So discriminator will try to automatically verify that whether this label represents a real normal, real attack, or fake attack, or fake normal data. So it tries to have 4 different labels automatically. And then discriminator takes input the real-time data which is coming to discriminator and try to make decision by applying this matrix, which is cross entropy loss, which has been used to measure the loss. So what happened here is that generator is over a period of time, the generator would be able to generate more good fake unlabeled data. On the other hand, discriminator will be able to learn to label this data more accurately. So they work in hand to hand with each other so that they both learn the appropriate labeling of the data. All this process is online learning because we continuously and keep on learning these models. This component was implemented as LSTM model, which is normally applied for time series data that we have in our case. And this is called data augmentation because this is the new data we produce. Plus we also automatically assign label to it. And then we increased the sample size because we always need more and more data to be more realistic. So we then, to prove that our digital twin model, so we did a lot of experiments, and we use this typically used machine learning quality metrics, which are precision, recall, and F1 scores. And we compared them with existing state-of-the-art method, and we found that our method was performing best. And one of the key result here actually is the last two rows here. So first we are saying attain without signal, and we're saying attain. Attain is the name of our method that we developed to learn and make anomaly detection with digital twin. So the attain without signal represents the results when we don't use digital twin component. And the attain is the one which has digital twin component also part of that this anomaly detection. And we found that attain actually managed to increase these scores or these machine learning quality metrics. So it means that digital twin was really helping to improve the anomaly detection capability in our case. So it gives a very positive results that digital twin have a benefit of using in these machine learning based methods. So this was our first result where we build a digital twin, we have anomaly detection with GAN and so on. But then we found that we could improve our digital twin much more. So in this case, we try to have this method which is called curriculum learning. This is another machine learning technique. So the basic idea is that when we learn in schools, usually we start with easy things, and then we add more complex thing and more complex thing and so on. So this process is called curriculum learning. So we applied that approach into our first work to further improve the anomaly detection capability. So if we look at this, so we have data initially coming from cyber physical system. So we change it to our curriculum learning method. And this curriculum learning method somehow applies different metrics that I will discuss later on briefly, and it produces sorted data. So previously we have the data, whatever we got, but in this case, we continuously sort the data according to difficulty level. And the idea is that we should use easy data first, and then we should use more difficult data at the second level. This is how it works. So then we implemented this approach. So this is the same diagram I showed before about digital twin model, where we use timed automata, we learned it, and then we fine tune it. This is a bottom component where we're doing anomaly detection, and this arrow again was the same as before. But this is a new component here we introduced, which is called curriculum learning, and it has two components. First is difficulty measure. So we were saying that we want to sort our data based on the difficulty level. So it means we need some sort of metrics to see that which sample is easy and which sample is difficult. There are many metrics exist, and we tried a lot of different things, but I can give an example that we can look at the complexity of the data, we can look at the distribution of the data, and we can look at the noise and how much each sample is more closer to anomaly to detection of a known attack, for example. So these kind of metrics we use to attach difficulty level with each sample of data. And we also, so these are the static measures. So we also use more dynamic measures where we continuously update the difficulty based on the new data when it comes based on different error metrics. So once we have this difficulty measure, which tries to see that which sample is more difficult, then we need to somehow schedule the training. So this component is called training scheduler. So what it does is that it takes input those samples and try to rearrange them. Again, there are many in the machine learning community. There are many different ways of doing it. So we experimented with different existing training schedulers, and we found that one of the baby step method was much more effective. What baby step training scheduler does is that it simply creates different buckets of different difficulty levels. Then each bucket, it puts a sample, which one is easy, little bit more difficult, little more difficult, and so on. So eventually we have these buckets, and then within the bucket, it uses to train the data. So this is called at the high level is called baby step training schedule. So we use 4 different difficulty measures combined with baby step training scheduler to sort the data. And then we use this sorting data with our discriminator. So it means that instead of getting the data as it is coming, we sort the data according to difficulty, and training schedulers has this capability of sorting it based on different metrics. And then we, of course, we need to prove that whether this curriculum learning can help our digital twin or not. So here you can see that we have 5 columns. Again, we use the same machine learning quality metrics such as precision recall to assess the quality of decisions or predictions made by our algorithm. And the last 2 columns shows the result of this method. So attain was our first work and this extension is latest. Just like in attain, we wanted to also assess whether using digital twin makes sense or not, whether it improves the quality or not. So S1 on the top shows our method without digital twin, and latest S2 shows with digital twin. And again, our observation was that in most of the cases, we managed to improve uh, the quality of anomaly detection with and without actually digital twin. Actually, digital twin was bringing more benefit in our case. So this gave us another positive result of our results. And then what we did was that we wanted to further deal with the evolution of digital twins. So in this case, what we did, we wanted to work on another real case study that we have. So in one of our EU project called Adaptness, we are working with this Spanish company called Orona, and Orona makes elevators. And on the right-hand side, you can see a typical elevator system. It consists of a set of elevators, and we have a set of floors. And at each floor, we have control panels, and control panels are used to control the elevator. You can call them, and you can, and so on. And then each elevator has a dedicated controller, and all these controllers, and the controller is responsible for the movement of the elevator up and down and so on. And all these components are connected via CAN bus, which is to the traffic master. And traffic master is the main component, which has a software component called dispatcher, which is responsible for efficient utilization of elevators so that people don't have to wait a long period of time. And those waiting times actually are used to measure the quality of service provided by each elevator. And sometimes this traffic master is also connected to Ethernet via access control, where you can implement more advanced security features. For example, if you want to restrict access to certain floor, you can implement all these criteria on a computer. So a lot of work that we do in the context with them is in software in the loop simulation testing, where they have real software, but the hardware is simulated. But we also have access to other data as well that we use. And they use this commercial tool Elevate for simulation purposes. So what we wanted to do. So this is our elevator from Orona. And one of the key components is the dispatcher. And dispatcher, what it does is that it sees at which time each passenger called the elevator, where from which floor to which floor the passenger wanted to go, and so on, and how much time, waiting time he or she has to take to wait for the elevator to come, and how much time it took to complete the journey, and so on. So it produces all this detailed set of data. And depending on the time of the day, we can see different patterns. For example, in the morning, let's say if your office is on the topmost floor, then it means that people will be in the 9 a.m., for example, if the office starts, people will be taking the elevators and going up. So this is called a peak traffic pattern. And then we have lunch peak, where people are, let's say, going to a bottom floor to take the lunch and coming back to their office. So different patterns that exist, and corresponding to each, we have the data available. And in this case, we wanted to predict average waiting time, which is one of the quality of service metrics which is used in this industry to measure that how good your software implementation for scheduler is. So we wanted to study, so there are different ways these elevators evolve, for example, but in this case, we studied on 2 different aspects. So we have elevator system, and it has an elevator simulator, for example. And then we have different version of dispatchers implemented by the company. So we have version 1, then version 2, version 3, and version 4. So the idea was that if we have a digital twin with one version implement, how can we transfer that knowledge to the second version, to the third version, instead of recreating the digital twin somehow to minimize the effort. And the second thing was that we have different traffic template. As I mentioned, that there is a up peak template where the traffic, everyone is going up. There is lunch peak where everyone is going to a certain floor and coming back, let's say after half an hour. So the second thing was that how can we transfer the knowledge from one that we learned from one traffic pattern into the another one within a digital twin, because then it can help us to minimize the cost of evolution. So we studied these two evolution in our this piece of work. So it's dispatcher evolution and traffic template evolution. So we use the concept of another machine learning technique, which is called transfer learning. So here we can see the same diagram that I presented before. So we have target cyber physical system in operation. And by target here, we mean that it could be target in terms of different dispatcher or different template where we want to transfer the knowledge to. And we have the target digital twin, then we have target digital twin model, and we have source digital twin capability, and these are interlinked. And then we have a source cyber physical system in operation in this case, which is from where we want to transfer the knowledge from source digital twin to target digital twin, something like this. So this is our aim, so that we can minimize, we can take care of the evolution instead of redoing things from the scratch. So this is roughly a sample looks like for our data in this case. So we have, let's say the passenger number 1, it wants to go from floor 1 to floor 6. Mass is, let's say 74 kilos, capacity of this is 75 and so on. So these are the different attributes associated with each passenger. And then the last 3 columns also show the times that we are interested in. For example, lift arrived at this particular time, which is lift 80 arrival time. The passenger arrived at destination in this particular time period. So it's the number looks strange, but these are somehow represent the time it take for the passenger to reach to his or her destination. So we studied these 4 scenarios for the transfer learning. So a best scenario means that we have the best dispatcher from the company, and we have up peak traffic pattern that we want to try out. And then we have lunch best, where we have the best dispatcher in terms of quality of service, and we have lunch peak traffic and so on. So the problems in evolutions were a few that we found that here. So like with any technique, there's always insufficient data available for ML model evolution. So for example, when we have a new version of a software deployed on the elevator, we will not have sufficient data available for it so that we can build its model. So it means somehow we need to rely on existing data and the transfer knowledge so that we can deal with this insufficiency of data. Second is the cost, which means that if you manually create model, it can always take much more time. So instead, we wanted to have more automated approach to reduce the cost. And then insufficient sources mean that there's always limited number of source digital twins from where we can transfer the knowledge. So to deal with this, we wanted to come up with this approach of transfer learning of digital twins. So we call this approach RICE-DT, or uncertainty aware transfer learning, and I will explain what I mean by uncertainty aware. Just like our Work1 and Work2, we build RICE-DT as a ML-based digital twin. So the structure is exactly the same, that we have a digital twin, it has a model, and that has some capability. The only difference here was that the capability that we were implementing was prediction of average waiting time, which is one of the quality of service attributes for elevators, a case study in this case. So our methodology. So this is a complex methodology. So our student, he implemented a lot of very advanced machine learning techniques, and a lot of the details I'm a bit unsure. So I'm not a machine learning guy. So what happened here is that at the top you see a box which is called uncertainty quantification. So what we discover is that the samples which are more uncertain, they have more interesting knowledge that should be transferred from source to target. So this means that uncertainty is a very important knowledge that should be transferred. So how to get that knowledge and how to see that which sample is more uncertain. So we So we applied this uncertainty quantification metrics, which is implemented in a toolbox called uncertainty toolbox module. And this module provides different metrics such as sharpness and so on that can help you to see that which sample has high degree of uncertainty associated with it. So we can have a number associated with each sample. So with those metrics, each data sample was also labeled as whether it is how uncertain it is. I think it was labeled, it was scaled between 0 and 1. So we sample the data, but then if we want to prioritize those uncertain samples for transfer learning, there was an issue with that. The issue was that if we pick just samples out of a time series data, it loses the contextual information, which is not good. So we had to solve that problem. So in the literature, they implement this technique, which is called multi-head attention module, which can somehow link the appropriate samples, which should also be transferred together so that we can keep the contextual information with each uncertain sample. So we applied this multi-head attention module in this case. Then you can see that we have a source digital twin capability, and we want to transfer it to target. We have to the target digital twin. So in the source, we have sequence module and let's say profile prediction and some other prediction capability. But the sequence module is the neural network model that we're implementing, which in this case was GRU, which is another machine learning model, which is applied to sequence data, which is time series. So, and below you can see that we have a target DTM with sequence module and the same components as well. So the assumption here is that the target digital twin will not have sufficient data, and that's why we want to transfer the knowledge from the source digital twin to the target digital twin. So what transfer learning here is does that it tries to minimize this loss between the two, between the source and the target, and it implements the conditional loss and marginal loss in this case. And conditional loss is related. So conditional loss is related to the distributions of the predictions. So we want to minimize the distance between the two distributions of predictions, and marginal loss is associated with data distribution. So we want to minimize both of distributions. So when we minimize the distributions, the common knowledge between the source and the digital twin will be minimized. And then we applied these kind of methods to transfer the knowledge from source digital twin to the target digital twin. So then we wanted to evaluate that whether it is beneficial actually to this transfer learning is bringing any benefit or not, whether uncertainty quantification is a good method or not. So we investigated 4 key research questions here. First research question was about, is it effective? Our approach is effective in transferring the knowledge from different traffic templates. For example, lunch to a peak template, for example. The second research question was that how effective our approach is in transferring the knowledge from different versions of software on the elevators. Third question was about, is uncertainty quantification really helps? Because our assumption was that if the uncertain sample contains more unique information that we should transfer, that can help in predictions or not. And finally, we also assessed a bit of time if we want to do these things manually or retraining the model, how much time it takes. So we also wanted to evaluate that aspect as well. So the results. So for the first two, as you can see that we found that when we transfer the knowledge across different traffic templates, we found that it really brought some benefits. So you can see that we measure this in terms of this one of the error metrics, which is called MSC. So by applying our transfer learning, we can reduce MSC quite a lot, which is a good result. And on the right bottom, you can see that we also transferred across different traffic templates from and we found that actually we also did statistical tests, and it showed that the quality was really improved, and actually transfer plus uncertainty quantification even further reduced the error, which is a very positive results. It means that transfer learning is working, plus transfer learning with uncertainty is also bringing some benefit. Now, looking at the other results, we also see that these are the key. So for up peak, for example, we see that, for example, this orange one is saying the best. The best one here means that the numbers of error from the best dispatcher, which was provided to us by the company. For that case, the error was higher, but for without uncertainty quantification and with uncertainty quantification, in most cases, we managed to reduce the error for up peak and lunch peak. Results were more actually better for somehow lunch peak, but still not very bad for up peak as well. So it also gives this indication that uncertainty quantification plus transfer learning is working. Then we also assessed some of the time costs. So we tried to see that, so we have pre-training cost, which is common. We always need that. And after that, we had the fine-tuning cost. And we found that the time, so without transfer here and with transfer, transfer per second. So these are 3 columns here. And we could see that without transfer means that if we have to retrain the model every time, it was 3.7 hours. And with transfer, it took 1.25 hours, plus transfer plus uncertainty quantification was a little bit higher. So in general, the cost is not that bad to apply this transfer learning, at least in this particular context. Finally, we wanted to do some additional analysis to see if there is a correlation between the uncertainty and the mean square error rates. And we found that they were strongly correlated. So there's more uncertainty, the more error it is there. So it means that by reducing the uncertainty, we can also reduce the error rate, which is also a very positive result, which say that we should consider uncertainty quantification while doing transfer learning, because it can reduce the uncertainty factor in the machine learning models that we used. So these were the 3 keywords in the same line of work. So we had first, we implemented a basic digital twin machine learning for anomaly detection. Then we improved its performance with curriculum learning. And then finally, we also take into consider the evolution in model in digital twins, where we transfer the knowledge across different digital twins. And the results are quite promising in our case. So what we are taking from there is that we are in part of this Adaptness EU project. We have access to a train control and management system. And we are trying to also assess how can we apply our methods to build digital twins in this case. So for example, train control management can have information about different systems like smoke detection, brake system, radio system, etc. And the idea is to take the data, signal data that comes from these systems and try to make some anomaly detection on that. So the next step for us that we are investing now is, together with Alstom in this case, is to build some machine learning based digital twin for anomaly detection for their case. So coming towards the conclusion. So in this work, we try to build digital twin with advanced machine learning techniques by taking into consider curriculum learning, transfer learning, GANs, and so on. And we also took into consider the model evolution aspect. So we, in the future works, we also trying to extend our case studies to more experiments so that we can have more confidence on the results. And other aspect that we want to investigate is that how can we combine these models with model-based system engineering? Because if we see that one of the challenge I presented was that when we build digital twin models only from the data, they don't capture those kind of spatial relationships between different sensors and actuators and those hardware components. So it means that that aspect is missing. So one thing that we want to do is also that if we can capture the initial structure of those things and some constraints and so on with those methods, and then we can also try to link the models learned from this machine learning together somehow to have more comprehensive digital twin models for anomaly detection or waiting time prediction and so on. So this is one of the other area that we want to study in the context of the same series of works. And then we are also want to apply to the additional case studies because I think we need to verify on the multiple things. So to this end, we have we have purchased a couple of autonomous rovers at Simula. So the idea is to also build their digital twin with machine learning plus model-based system engineering so that we can test our methods. And we're also working on one project with Oslo City, where we have access to some medical devices. For example, an example of these medical devices is medical dispensing machine. So it means that there's a machine and it is deployed at a patient's home, and it reminds patient to take medicine at the appropriate times and so on. But they have a variety of these kind of machines available and deployed in Oslo City to provide healthcare services. For example, people with the special diseases and so on. So our idea is also to make somehow those digital twins for autonomous rovers, plus those medical machines that we have access to, so that we can try out our methods and see how good, and to assess the benefits of digital twins in various contexts. So this is all I have. So, but I would also like to thank our collaborator on these projects. And part of these works were supported by Adaptness EU project. And Orona is our industrial partner in the project. It's a Spanish company who makes these elevators, who provided us the data and so on, so that we can do this research work. And this is mainly, once again, the PhD work of Xinhua, who implemented all these methods, did all the experiments, and worked with companies. So thank you very much. So now I'm open to take any questions from the audience.
Thank you very much, Shaukat. Let me give you one round of physical applause. I hope you can hear it. And yeah, let's open the floor for questions.